Yeah, sorry, I just muted my screen and I was just talking to myself. Sorry. Uh, Sorry there. Okay, cool. Sorry guys. Okay, so if I'm not audible clearly, or if I'm not, if the shade screen is not visible clearly, you have to let me know. Okay. I was talking to myself. Oh my god. Ah, cool. Fine then, guys. So let us begin now. Okay. So I hope I'm audible now, and the shade screen is visible clearly. Okay. Cool. Yeah. Awesome then. Good. Sending the poll here, and yeah, okay, so today might be the last class. Okay, I'll try to wind it up today, or like maybe if one or two concepts were worth of 5-10 minutes might be remaining from this chapter. Okay, so I'll be completing almost the chapter. 95% of the chapter of electromagnetic induction will be over today. Okay, so we are about to end the chapter, and since the Hyderabad region, like most of you who are in Zoom class, have exams for from 4th January, right? So we are just working out a plan. Whether can we conduct class during this time, or should we uh, just have a revision session? We are not sure yet. We are just working out the plan. We'll let you know soon what will be the plan. Okay. Um, and until then, so imagine from Wednesday I'm going to start a new chapter. So I'll be having Wednesday, um, right? So Wednesday you don't have class. Yeah. So Thursday we have one class, Friday we have one class. So we have only two classes for this week. So I thought of taking, uh, electromagnetic waves and what else? Communication systems. So this is one chapter, two chapters separately, but in Avanda it's one chapter. We could complete this very quick because like electromagnetic waves takes off like 60 minutes of theory, 30 minutes of problem. Even same with the communication system, 60 minutes of theory, 30 minutes of problem. It happens so we could complete this in 2 days. Okay, so we'll be done with these two chapters. But the problem is Friday is holiday because of New Year. Yeah, so Friday we do have holiday because of New Year. So we'll work it out, guys. Okay, no worries. Okay, apart from planning, we'll check the planning out. Okay, so we'll come back to the concepts what you're going to learn today. So today we're going to understand inductors. So we started right in the last class. We just had a brief discussion about what an inductor is, and and today we're going to see what is an LR circuit. If I remember, in the last chapter of current electricity, I thought most of you, right? I thought what was RC circuit. Do you remember RC circuit, guys? So RC circuit is a basically a charging. Like how do you charge a phone, or how do you charge my laptop? Right. Battery is a capacitor. Resistance is the wire. So this was how do we charge a battery, or how do we discharge a battery? We learned this already in the last class. So today we are going to see a new kind of circuit called LR circuit. Okay, where we have an inductor and a resistor together. Okay, so that's the concept which we're going to learn for today. And let me have a very quick revision of the concepts which you have understood till now. So till now, we have understood, if you remember, we know how an EMF is induced, and how a current is induced, or how a magnetic field B is induced. Okay, whenever there is change in flux. Okay, whenever magnetic flux changes, EMF is induced, current is induced, and as well as magnetic field is induced whenever flux changes, right? Similarly, whenever there is motion, of course, whenever there is motion of a rod in a magnetic field with velocity v, even then EMF, current, and a magnetic field is induced. And the third case, a rotation. Whenever this rod, है ना, if this rod doesn't move, but rather than it rotates with angular velocity omega, even then an EMF is induced. Okay, and we know the magnitudes. Okay, so what is the EMF induced for a flux change? For a flux change, EMF induced is minus d phi by dt, minus d phi by dt. And what is the EMF induced for a motional EMF, which is moving with linear velocity v? BVL, right? And what is the EMF induced for a rotation? Half B omega L square. So these are the EMFs which we know, right? So these are the respective EMFs induced. And if you want to find current, what do you do? If you want to find current, very simple step. If you know EMF, you know that EMF is equal to I into R, or current I is equal to EMF by resistance. If you just divide this EMF by resistance, you will get current. So this will be the induced current. Okay, guys. So very simple. This is induced current. Okay, cool, right? So we have to be very careful and understand the situation, whether the flux is changing, or is there any motion, or there is any rotation. We have to check for these clues from the question or the situation which is given. Then from that situation, we have to apply the formula. Okay, we have to be very careful while choosing the formula and applying the condition. We have to be very careful as much as possible. Okay. Okay, cool then. So these are things which I learned. Then if I know voltage, this one d phi by dt or BVL or half B omega square L, and if I know current, then I can find anything. I can find power, right? Power dissipated. I can find out energy lost in the circuit, and I can write how much force we have to apply. So we saw a few numericals in the last class also regarding force, how to calculate the force required, everything else, right? So the rest of all of things we can calculate very easily without any problem. Okay, so then coming back to today's topic, inductors. Okay, so inductors is called a circuit element. So what is circuit element? Circuit element is a thing like which we usually include in the circuit. Like what are the things when I write a diagram of a circuit? If you notice, guys, I do usually write there'll be a resistor, there'll be a capacitor, and now I'm going to write a third instrument called as an inductor, which is written like a solenoid, which is written like a solenoid, and one more circuit element is an EMF. So here in circuit, we can see four circuit elements. The first circuit element here is the resistance. The next circuit element is the capacitor. The new circuit element is the inductor L, capital L, and EMF is one of the most known circuit element. Okay. So we are going to talk today about an inductor. So how an inductor behaves, how to calculate the potential difference. What will be the potential difference across the inductor? What happens if I connect inductor in series? What happens if I connect inductor in parallel? Right, we're going to see such all of these things today. Cool, right? So I hope you are ready to begin, guys. Okay, are we cool? Shall we move ahead? Yeah, cool, right? Yeah. So you can click yes. Okay, good, awesome. So I hope you don't have any doubts. If you have any doubts regarding any of the previous concept, you can let me know in the chat box, or you can text me in the WhatsApp group of, you know, um, your perfect class. Yeah, that's correct, Madhavi. And you could also text me in Telegram group if you have any doubts that I need to clear for this YouTube, guys. Okay, good, guys, keep it up. Yeah, awesome. So let me introduce to the old circuit elements, right? So one of the first circuit element which we know is the resistor. What is a resistor? Resistor always prohibits the current, right? For example, if there's a lot of resistance in a circuit, the current flowing in the circuit will be less. If resistance is high, the current will be less. So it's like we always thought current and resistance are inversely proportional to each other, and we know that the formula which we use to calculate resistance is V is equal to IR. So this is the voltage drop because of a resistor, right? And resistors, we have learned how to calculate resistance series, parallel, what is color coding, what is power dissipated in the resistor, right? All of the basic things we already learned about resistor. And the next circuit element which I'll be telling you is the capacitor. So capacitor is something which stores. Resistor prohibits the current, and capacitors store the current. It will basically store the charge, and whenever that charge flows, current flows, right? So you can say it can store charge or it can store current. You can think of them in the same way. Okay. Prashant, you don't remember color coding, bro? I hope Pradeep sir have taught you because it comes in the previous chapter, bro. If you have not taught, I'll share you the video link in which I have taught color coding. You can go back to that. Okay, not a problem. Yeah. Okay. So then a capacitor shows its charge, which means current is flowing regularly, right? Therefore, Q is equal to CV is the formula which we use to find the charge stored by a capacitor, and also therefore we can find a potential difference. Okay, we can also find a potential difference, and later on, right? So we know what the new circuit element which we're going to learn is a basic simple circuit element which is called an inductor. So what is an inductor, guys? Inductor is very simple. Uh, it's just a coil. You take a regular coil. Okay, you take a regular coil. Then what you do is you rotate the regular coil. Okay, you make it coil. You loop the coil. Okay, you loop the coil in this particular way, and it becomes a particularly, a inductor. Very simple, right? So this is called an inductor. This is a conductor where there is no loop, and now this shape is called as an inductor. Very simple. Okay, this is an inductor. Cool, right? And there are two different shapes of inductor. One is called solenoid. solenoid, other is called toroid. Other is called toroid. So what is solenoid? Solenoid is a coiled wire. See, we have coiled the wire parallelly along a cylinder. If it is a cylindrical shape, it's called solenoid. If it is a circular shape, if it is coiled in a circular shape, it is called a toroid. So this we saw in the last class also. Okay, so there's a formula for resistance, there's a formula for capacitance. So is there a formula for inductance? How to find a potential drop? Yes, of course. And the formula is uh, exactly, that's correct, Nitank and Rajama. Very good. Okay, so and the formula is the potential drop can be calculated by using the drop EMF. The drop or the EMF generated is equal to minus of L di by dt. So we saw this formula, right, in the last class. I hope you remember. So this is the EMF generated or the drop across an inductor. Okay, so usually we use this formula. Okay, there is no derivation as like we never derived what is V is equal to IR, and we never derived what is Q is equal to CV, and there is no derivation again for what is EMF is equal to LDI by dt. But I have mentioned this formula already many of the times, right? Yeah. Okay. So the difference between inductor and conductor is very simple. Okay, what happens is, see, inductor there are no loops, so magnetic field will be just like always across this wire like this, right? But magnetic field for inductor is quite different. If you remember, I told you in the very initial class that the magnetic field of a solenoid is exactly similar to the magnetic field of a bar magnet. So conductor and inductor, they have different kinds of magnetic field. Okay, they have like very different kind of magnetic field, and that's the most important thing, because here all induction happens because change in magnetic field or magnetic flux, right? So since magnetic field of a conductor is very different from magnetic field of an inductor, those two are completely different. And similarly, toroid magnetic field is also very different. Is also very different. Okay, right? Cool. Okay, so guys, do you remember what self-inductance is? Do you remember from the last class? If you remember, click on yes. So what is self-inductance? Do you remember? Acha, very good. Okay. So inductance is very simple. Okay. So inductance, it's a different name saying that current is getting opposed. So opposition to current is called as inductance. Very simple. Okay. For example, if you take a single wire and a single conductor, okay, and if I pass current to the conductor, the current will pass through the conductor without any problem. Okay, agar if the resistance is very low, it will pass very easily. Okay, there is not at all a problem. But I'll change the situation very slightly now. What I have taken is I've taken this conductor and I have coiled this conductor into different shape like this. Okay, I've made it an inductor. So I made it an inductor. So what happens now is whenever some current is flowing through this wire, okay, as long it is in a straight way, it is not a problem. But when it starts to enter this loop will oppose the change in current. It will oppose the change in current, right? Now because this loop has a magnetic field of its own, and it is going to interact again with this current. But here no, here that doesn't happen because the magnetic field is going away outwards, so the current can go without any problem. There is no opposition from the magnetic field. But whenever in this situation, okay, in this kind of structure, there is always an opposition. There is always an opposition. Okay, so for very simple example, I'll give you two things. Okay, so first thing is the tungsten bulb or LED bulb. The tungsten bulb, there is wire. It is not a coiled wire. It's just a wire. So whenever current passes through it the bulb's on right now. It like when you click on the switch, the bulb on immediately, right? The bulb will get switched on immediately. So there is no delay in current. But when you pass through and when you switch on the tube light, it blinks, right? It blinks for some time, then it ons, because in tube light, in the circuit of tube light, we have kept a very big inductor. Okay, so just because not to destroy the bulb and make sure the air gets enough time to heat it up, so we use in an inductor. So what's happening here? When in a normal regular circuit, there is no opposition, the current flows right very soon, very clearly, very fastly. But in an inductor, there is an opposition to current. Okay, and this opposition is called as inductance. Okay, this opposition is called as inductance. Okay, cool, right? And how does it oppose? So for example, if the initial current I is flowing in this particular way, this circuit will create its own induced current, or will create its own induced current, and it will try to oppose this current I. Okay, so let me tell that a very big current I is flowing, and this inductor will give a very small current I dash, and it will try to oppose the change in current. It will try to oppose the change in current. Okay, so that's all. And this opposition is called as inductance. Whenever the circuit opposes the change in current, it is called as inductance. Okay, and there are two kinds of inductance. One is a self-inductance. Oh, spelling wrong. One is a self-inductance. Other is a mutual inductance. So what is a self-inductance? Self-inductance is a inductance happens in the same circuit. For example, here, if you notice, the current is flowing in the same circuit, and the induced current is also in the same circuit. If there is only one circuit, then it is called self-inductance. But if there are two circuits like this in the next diagram, or as I show you here, there are two circuits. You can see that magnetic field is changing in coil A, and the field is getting induced in coil B. So this kind of opposition due to current is called as mutual inductance. Very simple. Okay, self-inductance and mutual inductance. So let me have a very quick recall and revision of what I told you right now. Okay, in a conductor, the current will pass very smoothly without any problem. Okay, it passes very smoothly. But if you do any experiment using an inductor, then you notice there is some opposition. There is some opposition due to the shape, due to this particular shape, and particularly due to magnetic flux and magnetic field. थोड़ा uh, resistance hoga. Okay, cool, right? Then what happens is this kind of opposition we name it as inductance, and there are two kinds of inductance, that is called as self-inductance, which happens only in one coil, and there is mutual inductance, which happens in two coils. And now I'm going to talk you and tell you about self-inductance. Okay, and remember the potential difference due to an inductance C is EMF is equal to minus L di by dt. So whenever current changes now, so this is di by dt, change in current. I by dt is always change in current. So whenever current changes, this much EMF is induced. Okay, this much EMF is induced in the coil. Cool, right? So you should always be careful about it. If current is constant, agar di by dt constant, okay, then what will happen? EMF is zero, because if there is only di by dt present, only then there will be inductance or EMF change. Okay, agar if di by dt is equal to zero, then EMF is also equal to zero. So you should be very careful. The inductance occurs only when there is change in current. Only when there is change in current. Okay. How zero? For example, if you take alternating current is always changing. So di by dt is always present. Current is value is changing. So di by dt is always present for an alternating current. But if you take a DC current, okay, when you switch on, current will become from zero to some particular value, and direct current will stay constant. After some time, it becomes zero when you switch off. So you're on the switch, you're offing the switch here, and in between, it is constant. Current is constant. This is I versus T, current versus time, current versus time. See, in DC current, current is constant. When current is constant, that means di by dt is equal to zero, because differentiation of constant is always zero, right? So if you differentiate a constant value, you get zero current. I mean zero differentiation. So jab zero hoga. Okay. Therefore, EMF can be induced only when current is changing at this part and at this part. Current change हो रहा है ना? Only at this point I can get an induced EMF. Or if I take AC source, AC circuit में always I get di by dt. So always the EMF is getting induced. Okay. Cool, right? Am I clear, guys? Am I clear about this? So first point, what you have to be clear is you should be very clear about inductance. There is no inductance in this circuit, and there is inductance in this circuit. And one circuit may self-inductance, those circuit may mutual inductance. And the potential drop, what you get due to inductance is EMF is equal to minus L di by dt. And one most important point is, जब current change होगा, only at that time I have inductance, because I have to have di by dt some finite value. If I is constant, di by dt zero hoga, no EMF, no induced EMF. Okay. Am I clear about all these points? If I'm clear about this, I'll derive mutual inductance or self-inductance. Then I'll jump to derivation of mutual inductance. Am I clear, guys? Click on yes or no if I'm clear. Okay. So YouTube guys, am I clear? Zoom guys, yeah, cool. So YouTube guys, you can let me know in the chat box. Okay. So if you are clear, you can click on yes, sir. And text me yes. Okay. Cool guys, great, awesome. So the and the trick to derive the this L guys. Okay, let me explain this term. Okay, what is E here? E is called an the induced EMF. What is di by dt? Di by dt is a change in current. And what is L here? L is called inductance, right? L is called inductance. In case of mutual inductance, I denoted by letter M. L is self-inductance. Mutual inductance is denoted by letter M. Okay. So how to derive this formula? So first, the step is very simple. You start from the very known formula, Michael Faraday's formula. Okay. Okay, Uday, cool. Okay, Madhavi. So you You start from the first most important and easiest formula. The induced EMF is given as minus d phi by dt. Okay, this was one of the most easiest formula. This is back EMF, if you remember. Right? This is called the back EMF, and you start from this formula, and you solve this formula into different steps, and you'll come back to this formula lastly. Okay, this is our goal. So this is our initial point. Okay, then I'll come back to this formula. That's correct, Rajama. Very good. Okay, so what I do next is very simple. Since see, let me explain. Whenever I connect a solenoid to a battery, okay, and current I starts to flow, current I is entering the solenoid, and solenoid will now oppose the current because current B start हो रहा है ना flow करने के लिए. So current is starting to flow just now. So what happens is the current will oppose this current by inducing an EMF E. And let me say this solenoid has number of coils N. Total number of coil is N. Okay. So let me write it down here very clearly. N is total coils, total number of coils. And small n is total number of coils by length L, small l, okay. Total number of coil by L is called small n. Okay, so I hope you remember this, don't forget, okay. Okay, so then starting with the Faraday's formula, you have to notice that since there are n number of coils, I have to multiply this by n. Okay, so that is now this is the formula for back EMF, which I taught you in the last class also, right? So we have to be very careful. If there is only one coil, n is equal to 1. If there are many number of coils, n becomes those many number of coils. So this is the point where I start. Okay, and next point I know is flux phi. Okay, phi is equal to BA cos theta, and in this situation it is equal to BA, because see the magnetic field is going out of the solenoid, and area vector also points outside the solenoid. They are parallel to each other. Cos theta is equal to theta is equal to 0, and cos 0 becomes 1. Therefore flux is equal to B into A. Bas, ho gaya. Okay, and if you notice the magnetic field here is due to a solenoid. This is a solenoid, right? And can you tell me guys, what is the magnetic field due to solenoid? Do you remember? Anyone from YouTube or Zoom class? What is the magnetic field due to solenoid? I derived the formula for solenoid magnetic field, and also we have learned Biot-Savart law just as a revision in the last class, right? That's good. That's good. Very good. So magnetic field due to solenoid is given as mu naught n small I. That's good, Suchindra. Okay. So mu naught ni is a magnetic field due to solenoid. That's correct, Vandita. Very good. Okay. So this is what happens. Yes, good, cool. So this is the magnetic field due to solenoid. So let me plug it here. Instead of B, I'll write this formula. Therefore, my whole formula changes into magnetic flux phi is equal to what is B? B is equal to mu naught Ni into area. I'll write area as it is. So this is the formula for magnetic flux total. Okay. So lastly, what I do is I just use this formula and plug it back here in this phi here. Okay. Therefore, second step, EMF is equal to minus N I'll write as it is d by dt of what is phi, guys? Phi is mu naught Ni into area. Mu naught Ni into, yeah, that's correct, Madhavi also, right? Yeah. So what are the constants? Sorry, cap small n here. I forgot. Yeah, small n. Okay. So what are the constants here? Let me bring the constant outside. Okay, EMF as it is, minus n as it is. If I notice mu naught is a constant term, comes outside. Number of tons per unit length, n is constant, comes outside. Area is never changing. Area of solenoid remains always the same. So it comes outside. That's correct, Itanka. Good. And what is remaining? Di by dt. Current change or abhi. So di by dt. I'll keep current as it is. So I brought mu naught outside, n outside, I outside. Sorry, not I, A outside. Okay, guys, this is all. Now I can compare this with this formula. Okay, compare these two formula now. Left hand side EMF, EMF, cool. Right hand side negative, negative, cool. And there is d exactly good. Okay. So now what I do is I replace this whole formula, what I can see here, EMF as it is, and instead of this whole constant, I'll write it as letter L. Okay, I'll write this as letter L, and I'll write derivative as it is. Therefore, letter L will be equal to, what will be the value of letter L here? Inductance value. Exactly, inductance will be equal to N mu naught small n into area. Okay, yeah. Cool, right? So this will be the inductance, and this is the self-inductance, guys. For any coil, this is the value of self-inductance. Okay, and you can write it in many different forms. Not at all a problem. Okay, you can use these two relation here, and you can change it to numerous form. For example, one form is L is equal to N. I'll write it as it is. mu naught as it is. Small n can be written as n by length small l into area, or this can be written as n square mu naught a by l. So you can write in this particular way also. So that just it doesn't make a difference because they're all same formulas but in different format. Okay, that's correct, Pawan Kumar. But the denominator is L, bro. You have to be careful about it. Am I clear, guys? So I'll have a very quick recall of the derivation. Okay, it should be very pay attention. I'll do it very quick. I'll not repeat again and again. Not I'll not bore you out. Okay, so what's going to happen is very simple. What's going to happen is have a coil here. Okay, I have a coil here, very simple. And in this coil, whenever current flows, current starts to flow from 0 to some particular value I, there'll be change in current derivativity exists. Okay, then I know that EMF induced is equal to minus d phi by dt, right? And since there are a number of coils, I'll multiply this by n. Okay, where area is the uh, coil. I mean, the coil has an area A, and the total length is small l of this coil. Okay. So next, what happens is EMF is equal to minus n into d by dt of d into A. Flux is written as B into A because theta is equal to 0, cos theta is equal to 1. Therefore, EMF is equal to minus n as it is d by dt of the magnetic field of a solenoid here is mu naught ni into area A. Mu naught n and A are constant, so we bring them outside. So it becomes minus n into mu naught small n into area di by dt. Okay, that's all. And now I'll compare this formula with E is equal to minus L di by dt. Therefore, I easily notice that L is being replaced by this constant. Therefore, inductance L becomes mu naught n square A by L. Okay, cool, right? Am I clear, guys? So this is how we find self-inductance, and it's a constant value. It only depends on, if you notice very carefully, this only depends on number of coils. How many coils do we have? It depends on the length of the coil. It depends on area of the coil, and it depends on the permeability of the coil. Otherwise, it's a constant. If all of these doesn't change, the inductor value never changes. The inductance value never changes. It remains the constant all the time. Okay. So am I clear, guys? So if I'm clear, click on yes. Am I clear, YouTube guys? Am I clear, Zoom guys? Yeah, good then. Awesome. Great. Okay then. So once we know what is self-inductance, we can use the same formula, same steps, and we can derive mutual inductance. So what I have to do, I'll start from Faraday's law of self-induction or the back EMF formula. Then I'll substitute what is the magnetic field. Then I'll differentiate the magnetic field or the flux. Then I'll get mutual inductance in this case. Okay. So in this case, you should notice, guys, what happens in the mutual inductance. So mutual inductance is very simple. Give me a second here. How small L came? Acha. Bro, if you notice here, N is the total number of coil, capital N, and small n is written as total number of coils per unit length. That N, the small n is it's a different name. It's called the linear density. Okay, N by L, N by L. So what I do is, see here, I have N mu naught and small n. Instead of small n, I'll write it as capital N by L. Okay, so that is how L comes. Okay, yeah, cool, right? Okay. So coming back to the mutual inductance. So what happens to mutual inductance? So mutual inductance is the opposition given by an other coil, not by the same coil, but rather than the other coil. Now we have two different coils, coil A, coil B. If you notice this diagram, you can see the lamp A or the source A is connected to a source and current is flowing through this coil. And whenever current flows, magnetic field also flows. And in alternating current, magnetic field always changes because alternating current always changes. Whenever current changes, magnetic field also changes, right? And whenever magnetic field changes, which is linked to the coil B, which is near the coil B, then due to change in magnetic flux, an EMF is induced in coil B. Okay, so I'll repeat step by step, pay attention. So what happens is, see, in the first coil the bulb is always on because it is the source. The bulb is always on, right? Because I have kept a source here, I connected a battery, and current is flowing through this coil, and an AC current is flowing. And if you notice, AC current is flowing. In AC current, the current always changes. Therefore, magnetic field is also changing all the time, right? Magnetic field is also changing all the time. Very simple. Cool, right? So whenever magnetic field changes near this particular coil, see, whenever there is change in magnetic flux, an EMF is induced in this coil. The EMF induced होगा. Okay, before inducing again, according to Lenz's law, it will always try to oppose the induction. It will always try to oppose the induction, and that induction is called as mutual inductance. Mutual inductance. Okay, so I'll tell you two things which are very important here. The notations. Okay, so I'll call this as primary coil, and I'll call this as secondary coil. In primary coil, I've connected the battery. Current is coming from the primary battery, and current is induced in the secondary source, secondary circuit. Current is always induced in the secondary circuit. Cool, right? So, and what happens here is, let me tell that the number of coils in primary coil is N1, the area of the primary coil is A1, and the length of the primary coil is L. And number of turns in the secondary coil is N2. Number of turns in number of area, sorry, the area of the secondary coil is A2, and length of the secondary coil is L. I kept same L just to make the derivation simple. Have made the same length. So primary coil number of turns N1, area A1, length L. Secondary coil number of turns N2, area A2, length L. Okay, completed. So, okay, so you should be very careful in which coil. So I want all of you to answer me now. In which coil is the EMF is getting induced? Is it in coil 1 or in coil 2? In which coil am I getting the EMF? Okay, 1 or 2? Text faster. So is my coil getting induced in 1 or 2? Exactly. In coil 2, I'm getting the induced EMF, right? See, that's correct, Kavan. That's correct, Itanka Prashant. Good. So what's happening is current is flowing in the primary circuit constantly all the time, but current is getting induced, it's getting created or it's getting destroyed in the secondary coil. So I have to find or I have to use the Maxwell's formula for secondary coil. Okay, EMF induced in coil 2 is equal to minus how many number of turns are there in coil 2? N2 and d by dt of magnetic flux. Okay, so I'll ask you one more question. From which coil is the magnetic flux coming? Is it coming from the coil 1 or is it coming from the coil 2? From which coil? It's magnetic flux. So what is the source of magnetic flux? That's correct, Madhavi. Uday, good. Okay. Exactly. So magnetic flux is coming from coil 1. So this is how I read the formula. Flux from one change or hai. Okay, should be very careful about this. This is how we read the formula for mutual inductance. It is very easy in the old case. See, E is equal to minus N d phi by dt. There is no N1, N2, d phi, d phi, 1, 2. No, there is nothing there. But here you have to be very careful, okay? Because EMF is getting induced in coil 2. So that's why I've written EMF induced due to 2. And EMF induced due to 2 will depend on number of coils in coil 2. So I've written N2. And but the flux is coming from 1. So I've written it d phi 1. Okay, I hope I'm clear with this concept, right? Exactly, that's correct. Good, good guys. So this is how we write the E2 and N2 and d phi 1 by dt. Okay, so that's completed. That's all. If you understood this step now, derivation asan hoga, and we can derive any formula without any problem further on. So let me write E2 as it is without changing anything, N2 as it is, and d by dt of what is the flux due to solenoid? Same. See, coil 1 is also a solenoid, coil 2 is also a solenoid. So solenoid ka formula, as already many of you told you, it is let me write flux as b into a, b1 into a1. Flux 1 is equal to b1 into a1. So that's one step. Next, E2 is equal to minus N2 d by dt of what is b1? B1 is nothing but mu naught n1 I1. Right, mu naught Ni. As I already told all of you told in the previous slide, you told that magnetic field to solenoid is B is equal to B is equal to mu naught Ni. I'm doing the same thing here. B1 is equal to mu naught Ni, but 1 1. I'm writing 1 1 because it is B1 coming from coil 1. Okay, that's correct. And cos theta, that's correct. And cos theta here again, cos theta will become 1. Right, cos theta will become 1. Cool, right? So moving ahead very slowly, I'll let you bring out a constant outside. So E2 stays there itself, minus N2. See, N1 comes outside. So I'll bring N1 outside, negative there itself. N2 stays there. Area is constant. Okay, mu naught is constant, comes outside, but current is not constant because current is changing all the time. So I'll write d there itself. I'll leave it there without changing anything. Okay. So later on, as I move ahead, I'll since n1 is a constant, n2 is a constant value, area is a constant, mu naught is a constant, I'll write this by letter m, and the rest di by dt I'll write it as it is. Okay, and this m is called as mutual inductance. This m is called as mutual inductance, and it goes by the formula m is equal to minus small n1 capital N2 area and mu naught. or you can modify, like as we did modified in all the steps in the last class also. Small n can be done as capital N1 by small length L and N2 A mu naught. So this is the formula for mutual inductance, guys. Okay, very similar to last formula. If you notice, here we have N1, N2, A mu naught by L. Instead of N1, N2, I have N into N, right? N into N, N square. But here I have N1, N2. That's all. Okay, that's the only difference between mutual inductance and self-inductance. Okay. And again, if you notice, it's a constant value. It's a constant value because number of turns N1 is constant, N2 is constant, area is constant, mu naught is constant, length is constant. So all of them are same. Here M is also a constant value. But the most important concept here is to write the first formula. Okay, write the first formula. EMF is induced in the second coil. Induced happening in the second coil, but the flux is coming from the first coil. Okay, so that is why I'm writing phi1. Okay, because it's coming from the first coil, and phi1 is nothing but BA1. B is nothing but mu naught N1 I1 into area 1. Okay, and induced EMF E2 is equal to minus N2 into flux changes from 1 d phi 1 by dt. If you notice, if you write the first step very clearly, if you understand the first step very clearly, the remaining steps will be very simple. Okay, just expanding B as phi as BA cos theta, B expanding B as mu naught Ni, taking constant outside. Simple as that. Okay. So before going to the next concept, so let me write on the formula, both the formulas here. I think I can write it here. Yeah. So self-inductance is which happens in the same coil itself, and it is denoted by letter L. And self-inductance kya hoga? It is nothing but N square area mu naught by length L. Okay, and mutual inductance is what happens between two coils. So this has number of coils N, it has length L, and it has area A. Okay, and this is the formula. Next, if I have two different coils of N1 turns and one more coil of N2 turns, both of their length is L and both of their area is A2 and A1 respectively. So then I get the mutual inductance formula as, it was A1, right? Yeah, it was A1. Okay, all everywhere. Okay, so and it will become mutual inductance is equal to N1 into N2 into area 1 into mu naught by L. So this will be the mutual inductance formula, guys. So does L and M specific numerical value? Acha. So for example, what happens here is, Nitank, so what happens is, so you take a coil, you take a copper wire, you take a regular copper wire, and you wound it up only 3 or 4 coils, and in this particular way. Okay, this is one way you can coil it. Other is you will coil very strongly in this particular way. Okay, now can you tell me which will have more self-inductance? Which will have more self-inductance? I'll mark this as 1, I'll mark this as 2. 1 or 2. Okay, so of course that's correct, guys. 2 ka self inductance zyada hoga. 2 ka self inductance will be very high because it is huge number of tons, right? It has huge number of tons. And okay, so for better convenience, okay, instead of confusing you, let me give you a very simple example. Okay, so because you should not jump into higher problems right now. uh, yeah, so I take a copper wire, and I coil this in this particular shape, and I coil this in this particular way. Okay, so of course, when I compare the first and the second one, I'll get second one, since it has more number of turns, it will have higher inductance. Okay, but I'll write this as L1 and I'll write this as L2. L1 is a constant value, it never changes. L1 ka value is always same and L2 ka value is always same, but L2 is greater than L1. Okay, they are numbers. Inductance are just numbers. Okay, they might have units, they might not have units, but they are just numbers. Okay, they are just numbers. They won't change when I'm performing the experiment. Suddenly, iska value change nahi hoga. But while constructing it, while manufacturing it, I can change the value. Okay, I can change the value while manufacturing it. But once I manufacture, uska value is fixed. They won't change. Cool, right? So you can notice here that mutual inductance or self-inductance is inversely proportional to length. If length is more, inductance is less. If length is more, inductance is less. And it is directly proportional to N. So N zyada hoga, induction zyada hoga. If area is high, inductance is high. If mu naught is high, inductance is high. Okay, so you might have seen in some of your CBSE classes that inside a copper wire, they keep a magnet, right? They keep a conductor, or sorry, not a magnet, they keep an iron for generator or You might have seen this. If you have not seen this, don't worry. We'll come back to generator, right? And at that time, I'll explain this. Okay. So they keep a coil because to increase mu naught, because iron will have very good mu naught value. So that is why they do this. That's correct, bro. Yeah. Okay. And we'll come back to this. Okay. This is a topic not yet thought, and we'll come back to that. But remember, it's mu naught is important here because inductance is proportional to mu naught. Cool, right? Okay, then. So that's all about inductance, self-inductance, and mutual inductance. Uh, be careful about the formula. Don't forget the formula, and also remember the concept. Okay, which inductance, which flux you have to use for the derivation. Okay, cool, right? Okay, so I'll be asking you for any doubts. Do you have any doubts, guys? If you don't have any doubts, I'll move on to something called as eddy current, a new concept. Okay. So, any doubts? If you have any doubts, you can let me know. If you don't have any doubts, I will move forward. Okay, cool. No doubts. Acha. Great. That's great, right? But feel free to have doubts. Okay, if you have doubts, that's not a problem. Okay. Yeah. Okay. Yep. Cool then. So next, starting to solve eddy current. So I'm introducing a new concept called as eddy current. So guys, can you tell me what is eddy current? So I told you that whenever a magnetic flux changes inside a coil, few things happen. What happens is EMF is induced, right? Current is induced, and magnetic field is induced. So whenever EMF is induced, that is called as back EMF. That is called as back EMF. And whenever current is induced, that is called as eddy current, unwanted current. Yeah, exactly. It's called unwanted current. Very good, bro. So eddy current. Okay. So usually the opposition, the induced EMF always tries to oppose my current, right? So for example, a current is flowing inside this wire. Suddenly there's a coil, and the coil will give a small opposing current I dash, right? It is opposing the current. I don't want that. It is unnecessary. That is called as eddy current. Okay, and eddy current has lot of application. Okay, very high. But we'll see the application in a moment. But let me tell you what eddy current is. Eddy current is a regular current which is induced from the change in magnetic flux. If EMF is equal to BLV, I know that a current is equal to potential by resistance. Therefore, current becomes BLV by R. So this is a simple formula to calculate eddy current. Okay, so why the current opposes the motion, and how do I know this? Okay, let me explain with an example, with an experiment. Okay, so what you do, guys, is you take a magnet. Okay, you take a very strong magnet. If you go to internet and search for neodymium magnets, you get magnets, and they're really strong. Okay, so I'm taking neodymium magnets in three different situations. Okay, I'm taking neodymium magnets in three different situations. Okay, so first situation is very simple. I just drop it from a particular height. I'm holding magnet very high. I'll drop it. The magnet will fall to the ground with some velocity. All the potential energy is now converted to kinetic energy. Okay. So next, what I do is I'll take a bigger pipe. I'll take a bigger PVC pipe. Okay, a plastic pipe, and now I'll drop this magnet, neodymium magnet, inside a plastic pipe. No problem. It will also drop with certain velocity, and both of their velocity is same. If this falls with the 10 meter per second when it reaches the ground, this also falls at 10 meter per second without any problem. They fall at same height. That's correct. Okay. But now I'm going to just modify this experiment in a very simple way. What I do is I take a copper wire, not a magnet. If I take a metal wire or a magnetic wire or a magnetic pipe, okay, if for example, if I take iron pipe, the magnet will be attracted to iron. If I take a magnetic pipe, that magnet will be attracted to the magnet. So I'm taking a copper pipe. So copper pipe is not a good attractive thing to magnet. So I'll take the copper wire, and copper is a very good conductor also. Okay. Now I'll drop this magnetic neodymium magnet inside this copper pipe. Can you tell me what will happen? Will it come with the same velocity, or इसका velocity ज़्यादा होगा, और इसका velocity कम होगा? High, same, low. Which will be your options, guys? Come on, tell me. What do you think will happen? So will the magnet, when it reaches the ground, it will be having higher velocity than the 10, or same velocity, or it is slowed down? That's correct, everyone. Good answer. Okay, what happens is the magnet will slow down. Magnetic velocity बहुत कम होगा. Okay, so when it falls with some slower velocity like 6 meter per second or 4 meter per second. Okay, it happens. Okay, and why it happens is very simple reason. You already know this. Okay, how do you know this? Because remember, guys. So whenever there's a like one single coil, okay, and whenever I put a magnet inside the coil, what will happen? The induced current will try to oppose the motion. Now the induced current will try to oppose the motion. So since there is north pole here, here also a north pole will be induced. North pole will be induced such that to oppose the motion. So when it repels, its velocity come hoga. Due to repulsion, this slows down and velocity is lesser. So it falls at a very low velocity. It falls at a very low velocity. Okay, and what happens? The induced current in this coil is called as eddy current. The current which slows down this, or the regular current due to induction is called as eddy current I. Okay, very simple. This current is also eddy current I. Okay, this current is also eddy current I. We have given a different fancier name. That's all. So eddy current is the current which opposes the change in magnetic flux, which opposes change in magnet. Okay, so very simple. Take three situations. You drop a magnet in the air, it drops at certain velocity. You drop a magnet inside a PVC pipe, it drops again with the same velocity as that of air. But if you drop the magnet in a copper wire, what happens is um, the magnet slows down. The magnet slows down because due to opposition. What you see here is the opposition, right? So what happens here is there is a south pole, there's north pole, and this we have learned in the first concept, first chapter, if you remember. I'm sorry, the first class of my this particular chapter. Whenever you put a magnet inside a coil, it opposes the motion. The magnetic field is induced according to Lenz's law. If you remember Lenz's law, it always opposes the motion, right? By creating a magnetic field. So that is why, if you notice, if I use only mg is acting, only weight is acting downwards. Here, only weight is acting downwards. But here, in the copper wire, magnetic field is acting upwards and mg is acting downwards. They cancel out and it becomes slower. It becomes slower. Okay, cool, right? So, and this the current which slows down is called as eddy current. And the formula is very simple, which is like if you know the EMF, you divide by resistance, current mil jayega. Cool, right? And this is called as eddy current. Okay, one more question. I'll ask you one more question. For example, if it is falling at 10 meters per second, it will have some kinetic energy. Here also it has the same kinetic energy, but here it has a less kinetic energy. So what happens to the other kinetic energy? Can you tell me? Energy is not getting conserved here. Energy is lost, right? So what happens to the remaining energy? Where is it? So if you drop a magnet, it is coming at certain velocity in the air. In the PVC also, it's coming with the same velocity. So energy is conserved. Okay. But when I put it in the copper tube, it falls with a slow velocity. Kinetic energy is lesser now. So what will happen to the remaining energy? Can you tell? Can anybody tell me? So where did that energy go? Where is it hiding? Exactly. That's right. Okay. So since the current is induced in the copper wire, and copper wire, of course, will have resistance, the energy is lost in the form of heat. Energy is lost in the form of heat. Very simple. So whenever, let me tell you guys, so whenever current flows in this copper wire, eddy current I flows, right? And of course, the copper will have resistance. Therefore, the energy dissipated will be equal to, or the power dissipated will be equal to I square R, or energy or heat energy dissipated will be equal to I square RT. So this much amount of heat is generated, or this much amount of power is lost in a coil which is carrying current I. Okay. So, but for example, I'm just talking about magnets, right? But why do I want to know the resistance? Okay. For example, if they don't give the resistance, then how do you calculate in terms of inductance? So, in terms of inductance, we can calculate the heat lost in a very simple manner without any problem. Okay. So let me write the same formula here. The heat lost by a small element dH is equal to I square RT, or I square R dt. I'll write it as dt. Okay. Or I can use any formula if you remember, right? Instead of I square R, I can write it as VI, that is EMF into I, or I can use EMF E square by R. I can use any formula. I'll use this formula because integration will be easier if I use this formula. Okay. So I'll modify this as DH is equal to EMF into current I into dt. So this is the formula I'll try to use because it is very easier, because I know the EMF induced. EMF so pata hai mere ko. So that's why I try to use this formula. Okay. So DH, his small heat dissipated is equal to what is the EMF due to the coil. So since this coil is opposing, Since this coil has a current, it will of course have an EMF, and that EMF is equal to L di by dt. I'm not writing negative because energy is a scalar quantity. Since energy is scalar, negative doesn't make much more of a sense. For vector, negative means if this is positive in direction, this becomes negative in direction. They're opposite to each other. But in scalars, negative doesn't make any sense. Energy is a scalar quantity, so I'll not write the sign. Okay. So EMF is equal to L di by dt, and I'll write I as it is, dt as it is. Dt cancel ho gaya. That's correct, Pawan Kumar. You derived the formula. Good. Okay. So what happens is now I'm left with two simple formulas. dH is equal to L into I into di. So if I want total heat now, I have to integrate this. If I want to total heat dissipated, I want um, to integrate this formula. dH ka integration heat h hoga, and L is a constant value, as I already told you. L comes outside, and I'm left with the integration of L into di. So what is the integration of x dx? It is x square by 2. Right. Similarly, what is the integration of I di? It is I square by 2. Okay. Therefore, this whole formula becomes h is equal to L into I square by 2 half Li square. So this is the amount of heat dissipated or heat lost in a coil or due to eddy currents. So this is the amount of heat which we always lose due to eddy current. Okay. So I hope you're clear. Very simple. Why I did not consider the sign? Because it's a scalar quantity. And why I prefer this formula? Because it is very easy to integrate. Okay. If I use this formula, I don't have information about current. If I use this formula, I have to square the EMF. Thoda mushkil hoga. But if I use this formula, I can get easy derivation. Okay. Yeah. So this is the heat dissipated instead of inductance. So what we have learned till now today. So till now we have learned that what is self-inductance, what is mutual inductance, and what is the heat dissipated inside a coil. Okay. So I'll perform the integration one more time. Be careful. Okay. Acha, eddy current one more time. So I'll revise the whole thing. Okay. Whenever you take a conductor, not just a copper tube or whenever you take a solenoid or a copper tube, and whenever you put a magnet inside it, it goes slowly. It goes very slowly inside rather than how it goes in the usual time. It goes slowly. Okay. It goes slowly because of the opposition created by the induced magnetic field. So induced magnetic field will create opposition. Okay, and that is why it slows down. And that current, okay, whenever magnetic field is induced and EMF is induced, whenever EMF is induced, our current is also induced. And this induced current I is called as eddy current. That's all. This induced current is called as eddy current. And if you know the EMF, you divide the EMF by R, you get the induced current. Very simple. Okay. And remaining, it is slowing down, and the kinetic energy will be lesser because the remaining energy is lost in the form of heat by half Li square. This much amount of heat is lost. Cool, right? Yeah. Okay. Eddy current derivation asked in board. I'm not sure, bro. They might ask because it's a very simple derivation. Okay. This thing is do there in the NCRT book. If you check, they do have the derivation in NCRT book, but I am not sure whether they have asked in board exams. Okay. Cool. Okay. So then where do we use this? For example, we use this in an induction coil, okay, induction stove. If you have an electric stove in your home, this exactly works in the principle of an induction. Okay. What happens is if you open the coil by any chance, don't open if everything is all right. If there's something to repair and if it is out of warranty, you can open the induction coil. When you open the induction coil, you notice the copper coil, okay, in this particular shape. They keep this coil, and whenever current passes through this coil, an opposing current, eddy current is created, and that eddy current will create heat, and we use that heat to cook our food, right, or water. That is how an induction coil cooks. And also in train, we use this for braking system. If you go to internet, if you go to YouTube and click on magnetic braking system, you'll understand, and they show you very beautiful videos. There are very good, beautiful videos on magnetic braking. So what happens is same thing. Okay. So here, if you notice, guys, the kinetic energy is lost, right? The kinetic energy was lost in kinetic energy. Same thing when a train wheel, you know that all the train wheels are metal, right? When the train wheel are rotating with very high velocity, and whenever I switch on the magnetic field, I use electromagnet and switch on the magnetic field as I showing here in this diagram, this kinetic energy will be lost in the form of heat. It becomes very hot. It becomes very hot. Okay, but it slows down, and that's a braking system we usually use in train, and that is why they are not faster also. Okay, they're slower because the kinetic energy will not lost instantly, but rather slowly. The kinetic energy is lost very slowly. That is why the brakes are slow, but the brakes are very efficient. Okay, they can take heavy amount of load. If I use my rubber brakes as we use in cycle, or hydraulic brakes as we use in um, particularly bikes, they might get, they're not long durable. Okay, they will be tested very soon. But it's magnetic, they are very durable, they stay for very longer times, and they can take very huge amount of load. Okay, so hydraulic brakes can take heavy amount of load, but they won't stay for longer time. Okay, but why we use magnetic brakes and strain is because of this reason. They can take huge amount of load, and they work all the time. They work all the time. Cool, right? So these are few applications. So if they ask in board exam, they won't ask you in JE. If they ask in board exam, you have to mention that we use eddy currents or heat generated by eddy currents in cooking of induction coils and in magnetic braking systems. Okay, cool, right? Yeah. Okay, so before this magnetic brakes, hydraulics brakes were used. Uh, Hydraulics were not new, bro. Magnetic brakes in the steam engines or the old train, because all these things were happening in the 18th century. Okay, so all this thing, 18th and 19th century, magnetic brakes were created, hydraulics were created. Hydraulics were very later on. They comes a bit slower. Okay, before them used to use manual brakes by using rubber and friction of regular things. Okay, but that was not so efficient. Cool. Okay. So that's all. Like that's all for that application of eddy current and heat generated, heat lost by the eddy current. Now let me talk a few things about RL circuit. So we'll come back to RL circuit, guys. If this is done, almost most of the chapter is over. Okay, so the last concept of chapter, the last important concept of the chapter is LR circuit. So okay, so let me tell you, whenever current flows through an resistor, V is equal to IR. So this much amount of potential is dropped. Whenever current I passes through a capacitor, how much potential is dropped? V is equal to Q by C. Q is equal to CV, or V is equal to Q by C. So this much amount of potential is dropped or gained, right? Depending on the situation, this much amount is dropped or gained. And similarly, whenever a current is passing through an inductor, how much amount of EMF is dropped? So I can say that EMF is equal to L di by dt, right? Or yeah, this much amount of EMF is dropped. Okay, in an inductor, this much amount of EMF should drop. So these are three important formula. You have to be very careful. You have to remember all these three formulas all the time. If you know these three formulas, you can, and if you know Kirchhoff's voltage law, and if you know Kirchhoff's current law, you can apply this concept for any circuit, and you can solve it very easily. And along with, you should be very strong at integration and differentiation. Okay, so then you can solve any circuit for any variable. आराम से हो जाएगा. So EMF lost in a battery is IR, EMF lost in capacitor is Q by C, and EMF lost or gained in a in an inductor is L di by dt. L di by dt. Okay. So and one more concept which is very important before I apply Kirchhoff law is, for example, when the current is increasing. Imagine I just switched on now. अभी switch on किया. So current is growing in the circuit. जब current is growing in the circuit, what will happen? So current is increasing now. I is increasing. So the induced current will try to oppose it. Will try to oppose the increase. अगर increase हो रहा है तो induced will decrease the current. Na? So it is trying to oppose it. So then I can write this as in this particular shape, because current is opposing. It is going exactly opposite. So I can write in case of increasing current, I can write in this particular way. Okay. Similarly, if the current is decreasing in circuit, if I switch off now, off किया तो current decrease होता है ना. So when current is decreasing now, so current का value कम हो रहा है, current is decreasing now. So what does the inductor do? Inductor will try to increase the current. Okay, and now I can arrange this in the same direction of that current, because current is decreasing. Now the induced current is trying to increase the decreasing current. Okay, you should be very careful about these two concepts. Okay, because see, positive terminal and negative terminals are exactly opposite. So one is gain, other is drop. You should be very careful. When current is increasing, okay, the inductor will try to oppose the motion. The inductor will try to oppose the current. Okay, when current is opposing, they're exactly in opposite direction. Okay, so this is a keyword. When it is opposing, you have to take the sign opposite to the induction current. The current is original current is towards right, the opposition current is towards left, because the current is increasing. They have to cancel out. They have to decrease themselves. Okay, that is why I do like this. Okay, in the next case, when current is decreasing, current is in this direction, but it is decreasing. When it is decreasing, what will happen? The induced EMF will try to increase the current, so they have in the same direction. Both of them will add now. The net will be adding, right? So decrease or increase होना चाहिए. Okay, and when this is the direction of current, you can, that means see, if I only write my induced EMF in this particular direction, current is coming out of the battery, and only if I write the current which is going in this direction, I have to write it in this particular way. Okay, yeah. So let me make you clear one more time. If you are clear with this concept, you can understand the LR circuit very easily. So imagine I switch on. जब switch on किया, current initially was 0 amperes, and now it is becoming 2 ampere, 6 ampere. The current is growing, right? Whenever the current is growing in the circuit, the inductor will oppose. जब increase हो रहा है, the inductor will try to decrease it, right? So when current is flowing in this direction, original current is flowing in this direction, the induced current will flow in the opposite direction to reduce it. Okay. At that time, the EMF of the inductor L di by dt is written with this kind of particular polarity. Okay, this is the polarity of increasing batteries. So next station, now I'm offing it. Like I switch off. जब मैंने off किया current को 2 ampere से it will reduce to 0 ampere, right? So when current is decreasing, what will the inductor do? Inductor will try to increase the current. So what happens is, this is the inductor, current is decreasing, but now the EMF is induced in such a way that it has to increase the current. So current will start to flow in this direction. It will start to flow in this direction. And if it is flowing in this direction, that means this is the direction of battery, because always current comes out to the positive terminal. See, current is going in this direction. So therefore, the positive terminal is the current aana chahiye. Always the current comes out of positive terminal. So you should be very careful about it. If current is flowing towards left, that means positive terminal is towards left. If current is flowing towards right, that means the positive terminal is towards right. हो गया बस. Okay, then the EMF of this is LdA by dt, same formula, but if I have to give the polarity depending on the direction of current. Okay, am I clear, guys? Am I clear? Click on yes or no. So depending on the direction of induced current, have to give the polarity of the battery depending on the direction of the magnitude is always same. The magnitude is always LdA by dt. It doesn't change. The magnitude never changes. Okay, the magnitude stays the same, only the polarity. Okay, so I'll tell you one more time, so pay very close attention. Okay, so जब current increase हो रहा है from 0 ampere to 2 ampere, current is increasing. When current is increasing, what will happen? The induced EMF has to decrease according to Lenz's law. Remember Lenz's law? Whenever current is increasing, induced EMF will decrease the current. So they have to act in opposite direction. Only then they can cancel out. That will decrease and they have to cancel out. So that is why current is going exactly opposite to the original current. Oh yeah, simple. And next case, when I switch off this circuit, the current will reduce from 2 ampere to 0 ampere. Current come हो रहा है. When current is reducing, my induced EMF will try to increase the current. Again, Lenz's law. Remember Lenz's law, okay? Always try to oppose the change. So current is reducing now. So to increase the current, the induced current will flow in the same direction. Now see, they add up and increase हो रहा है. So initially it was decreasing, but the net result is increasing here. Now the current was increasing here, but the net result is decreasing. Bas, okay. Am I clear, guys? Am I clear now? So once you know the direction of current, you can give the direction of battery. Okay, yeah. So if current is going in this direction, for example, if current is going in this direction, that means battery is in this direction. Okay, if current is going in this direction, battery is in this direction. Cool. Cool, right? Yeah, click on yes or no, guys, if I've understood. Okay, great then. Awesome. Cool, guys. Then cool. Okay, so we can apply the Kirchhoff law for a LR circuit. So LR circuit is a very simple circuit. What happens is when inductor L, our resistor R with a battery. So for charging, I do with respect to battery. YouTube guys, am I clear? Okay. Without battery, that is called as discharging. With battery, it is called as charging, and without battery, it is called as discharging. Okay. So now, when I switch on at time t is equal to 0, current I is equal to 0. After some, now I'm connecting the circuit. When I connect the circuit, क्या हो रहा है? Current will increase. जब current is increased in circuit, the original current is flowing in this direction. The original current is flowing in this direction. Now this has to oppose the current, right? So it will give opposing current in this direction. Induced current will be flowing in this direction. Okay, so I can modify whole circuit in a very simple way to apply Kirchhoff's law. So I'll write the voltage EMF E particularly in this direction only without changing anything. There is nothing in the top. There is resistance here, completely fine. And now, due to the inductor, the induced EMF is in this particular polarity because the opposing current is flowing in the opposite direction. जब increase हो रहा है, decrease होना चाहिए ना. So in this particular, it is passing it. So this is positive terminal, negative terminal, positive terminal, negative terminal. So we'll apply it, guys. So the total current, the total big current is passing in this direction. Total current is passing in this direction, right? So let us apply Kirchhoff junction law now. Oh, sorry, Kirchhoff's loop law. Okay, so let me choose any arbitrary direction. I'll choose anti-clockwise direction. So I'll start from this point. Okay, so guys, tell me when I move from this terminal to this terminal, will the potential increase or drop? Is there a gain in potential or drop in potential when I go from this direction to this direction? Will the potential gain or drop? Gain, because I'm moving from negative terminal to positive terminal. If you have some negative value, then you go to positive value, you're increasing the potential. Potential is increasing. So therefore, plus VR, potential increase or sorry, plus V. Okay. So plus EMF. Is gaining. It's a gain in EMF, so I'm writing it as positive. So it should be gain. So when we go from negative to positive, it is gain because imagine I had negative value, then I get positive value. That means I have gained the value now. So potential gain ho raha hai. Cool. And come back to this point. And from this point to this point, there is nothing. There is no circuit element. There is no change in EMF. And when I come from this point to this point, क्या हो रहा है? Current is flowing in the same direction. Current is flowing in this direction, and I am also moving in the same direction. So what will happen now? Gain or drop? What will happen with the resistor? Resistor में potential always drops along the direction of current. Okay, current will eat the resistor will eat up the potential. If you remember, it will eat up the potential. Therefore, potential will drop at the resistor. That's correct, Nitank and Rakesh. Good. So potential will drop at the resistor. हो गया. Okay. Later on, as I move from negative end of this point here, from this point to this point, I'm moving now. So what will happen when I move from positive to negative end of the inductor? So I'm moving from positive end to negative end. I had some positive value, then it is becoming negative. So I'm dropping the value, right? Value drop ho raha hai. Very good. So there is some drop at inductor. So minus VL is equal to 0. That's correct, Nikita, Pallavi, Pawan Kumar, Nitanka. Good. Okay. So what happens next is very simple. Expand the formula. Integrated ho jayega bas. Okay. So let me expand the formula and integrate it. I hope you are very good at integration. Okay. So EMF, I'll let EMF as it is. Potential drop at resistor is V is equal to IR. I'm writing the formula which I already told you to use. V is equal to IR at resistor. I'll use this formula. And potential drop at inductor is L di by dt. So minus L di by dt. I want current now. Okay, I want to find the total value of current. I want to find the equation for current. So let me rearrange this. Okay. So E minus IR, I'll keep it there itself, is equal to minus L di by dt to the left hand side, to the right hand side becomes plus L di by dt. Cool, fine. So dt, I'll send it to the numerator, L to the denominator, and E minus IR to the denominator. Okay, so dt I've sent it to the numerator, L to the denominator, and the di stays there, and E minus IR comes outside. Okay, so I can perform the integration now, but I'll make a very small calculation here. So I'll multiply this by R and I'll divide this equation by R. So I'm dividing the denominator by R and multiplying the same denominator by R. So there is no change in the value. Okay, so what I do next is I'll bring this R here. Okay, so what happens now? So this whole formula looks like, now blue is not a good color. Yeah, so let me take black. So this R goes up, becomes R in the numerator, dt there itself, L also denominator. That's completely fine. Is equal to di stays there without any change, divided by. So this R I have taken to the numerator, so I'll divide this R to the E and I'll divide this to the R by I by R. Okay, so this becomes E by R and this becomes I by R becomes I. So this is the formula, guys. This is the final formula which I get. Only thing is left is integration. Okay, so I have to integrate this whole formula. I integrate this formula. If I integrate, I get the formula for current. Okay, so time t is equal to 0. current is also equal to 0. So here t hai na, so that is why I put time t is equal to 0. Current here I have, so current is 0. After some time t, current is some current I. बस हो गया, लिमिट भी मिल गया, बस इंटीग्रेशन बाकी है. Okay, so let me write on the formula. At time t is equal to 0, after some time t, the constant is L by R, and the variable is dt is equal to integration di. At time t is equal to 0, current is 0. After some time t, current is I, divided by E by R minus I. So if you remember, guys, integration of why I'm writing constant. Integration of di by I is ln I. If you remember, integration of di by I is the ln I, right? So if I use the same substitution rule and if I apply it here, I get the integration very easily. I'll skip the integration step, but but again, derivation is not important here. But I believe that you can do the integration by yourself. Okay, so dt LR is R by L is constant, comes outside. Dt integration is t, completely fine, not a problem. Is equal to, this whole integration becomes minus ln E by R minus I, okay, minus I, lower limit is 0, upper limit is I. So this is what happens after the integration. So I'm just skipping out the step. I hope be careful about the integration. Try to practice when you go home. If you don't understand the integration, you can text me anytime. I'll help you out with the integration. Okay, I'm just skipping the integration part because it's quite easy, and it'll take some time. That's the issue. Okay, guys, but it's easy. You can use the substitution rule and you can derive it. So I'm skipping out the integration part, and you can take this as a homework. Try the integration by yourself. Okay. So after this, let me apply the limits. First, instead of I have to put I. Later on, I subtract instead of I with 0 value. So I'll write RT by L as it is. Okay, negative, I'll bring it here to the left hand side, is equal to ln of E by R minus, first time I'll put I, no problem, negative of ln of E by R. Instead of I have to put 0 as the lower limit. Completely fine. So this is RT by L, that's completely fine, no change there. Okay, is equal to ln A minus B can be written as ln A by B. So ln of A is, the first term is E minus E by R by I, divided by E by R. E by R. So this is how the ln rearranges itself. Okay. After this rearrangement of ln, we can shift the ln to this side. If the ln is shifting from this side to this side, it becomes exponential. I hope you remember, it becomes exponential. Exponential RT by L is equal to E by R minus I by E by R. So this is how the formula becomes. Okay, this is how it becomes. And if you remember, guys, what is E by R can be written as I naught, because EMF is constant. This EMF, this is constant. Resistance is constant. Therefore, E by R is equal to I naught. I is equal to V is equal to IR. So I use the same formula. I'll just multiply. I just substitute this E by R as I naught. So this whole formula looks like I naught minus I by I naught. It will become this particular way. Cool, right? Last substitution, last rearrangement. What happens is I'll bring this I naught to this side. Okay, so this becomes I naught into E minus RT by L, completely fine, is equal to I naught minus I as it is. So this I naught have brought to the numerator. And last step is I'll bring the negative I becomes positive I. Negative I naught stays there. Minus negative I naught comes to the right hand side, becomes e raised to minus RT by L. Okay. Now if I take I naught common, I will left with 1 minus e raised to T R by L. So this is the formula for current during the charging of an RL circuit. So the derivation is not important from the aspect of JEE, but you should remember the formula. Whenever they ask you a formula, you should remember this. Okay. So try to remember the formula, guys. So this derivation, I hope Pradeep sir also have done for capacitor, right? For RC circuit. The same derivation. There is no change in the derivation. There is no change at all. Almost the formula is completely same. But instead of R by L, you have by RC. By RC, right? Yeah. So you should be very careful about the formula. So try to understand it. Okay. So only one thing I did was I just kept the integration step, but everything I've shown you very carefully. So remember this formula. Okay. So this is the formula for current while charging an RL circuit. Current while charging an RL circuit. Similarly, we can also do the discharging, and it's very, very easy. It's not as tough as this, but it's very easy if you do for this particular circuit. Okay. So while discharging, guys, you should know that there is no battery while discharging, right? There will be no charge at all. There will be no battery at all, and current will flow from inductor. Current is flowing from inductor to the resistor. So now I'll rearrange the circuit in a simple way. So I'll write this resistance R as it is, and inductor I'll write it as in this particular shape. Okay, ho gaya, bas. Okay. So this is the last concept for today. So pay attention for some time. 5 minutes, I'll finish it off. So current is flowing from the battery from positive terminal, and it's going towards the resistor. Okay, so let me take the same direction. Okay. So only the difference is there is no battery. Here I had a battery, here I don't have a battery, and current is coming from the inductor. Okay. So let me start from this point. As I move from this point to this point, I'm moving from negative to positive. So gain at inductor. So potential will gain at inductor. Okay. And as I move along the direction of current through a resistor, potential drop at the resistor. It is equal to 0. Therefore, VL is equal to VR. And what is VL? VL is equal to L di by dt is equal to what is R? R is equal to IR. बस इसको integrate किया तो बस हो गया. Okay, not at all a problem. But one most important concept here is, जब there is no external EMF, when I don't have any external EMF, okay, Nitanka, just a minute, bro. When I don't have any external EMF, what will happen is the current will reduce. Because current is flowing from the inductor and there is a resistor, what will happen? The resistor will eat up all the current and current will reduce. Since the current is getting reduced, I'll put negative sign because di by dt is reducing. Okay, di by dt is reducing. So I put a negative sign. Okay, why I put a negative sign by myself? Because current is reducing. Whenever it is reducing, you have to put same thing. What happened in the last chapter in the RC circuit also? Whenever charge is reducing, you have to put negative sign there also. So put the negative sign. Ho gaya. So L there itself. Okay. No. I'll small modification here. I'll get the answer very easily. So what's the modification is? You rearrange it. It's rearrangement. आराम से answer मिल जाएगा. Di stays there itself. I brings to the numerator. Sorry, I brings to the denominator. Then rearrange it. R stays there. L comes to the denominator. Okay, and dt goes to the numerator, and negative signs stay here. Okay, so put the integration. Okay, guys, that's all. Okay, so the limits will be at time t is equal to 0. There was very good amount of current, maximum current था circuit में. After some time t, current reduces to current I, some value I. इसको integrate किया तो di by di integration is ln I. Okay, lower limit is I naught, upper limit is I is equal to minus RL constants comes outside. Integration of dt is t. बस हो गया. Okay, so then this becomes ln I by I naught. Okay, this becomes ln I by I naught because ln I minus ln I naught is ln I by I naught is equal to minus RL by T. So this is the formula what you get. Only step which is remaining is you send the ln to right hand side, it becomes exponential. Okay, so therefore I by I naught is equal to ln, sorry, exponential, right? When I bring it to right hand side, it becomes exponential minus R L by T, or final step I is equal to I naught into e raised to minus RLT, RL into T. So this is the formula for discharging current. This is the formula for discharging of a current. See, both the formulas are exactly same, but here I have I minus I naught e raised to T by RT by L, but here I just have I naught into minus RL by T. And why the current reduces? Because since there is no battery and there is only energy stored at inductor, and all the remaining current will be eaten up by this resistor. If you know that resistor will dissipate amount of energy in form of heat, right? So current will keep on reducing. After some time, there is nothing happening. कुछ भी नहीं होता है. Okay, all the current will be eaten up by the resistor. That's why current is reducing. So that's why I put negative sign. Cool, right? So this is the formula for charging and discharging of a circuit. So let me write them down here. What is charging? The charging current. Charging current is I 1 minus E into minus time by R and L. Okay, same formula. Here also get the same formula, but okay, bro, cool. So same thing happens here. Discharging current will be equal to I naught into e raised to minus T by R into L. So this will be discharging current, guys. That's all. Cool, right? Yeah. So this is discharging and charging. Am I clear, guys? So if I'm clear, click on yes. If you still have any doubts, you can, sir, I didn't understand this step, or ये concept miss हो रहा है. You can tell me and I'll explain that concept now. Am I clear, guys? So be careful about these two derivations because this repeats all the time. So in the capacitor chapter, you should have done it for R and C, and in inductor chapter, I have done it for R and L. And when I go to this chapter, particularly AC circuit, I will be doing it for RC, RL, LC, and LCR. I'll be doing it for all these four different circuit elements. So you should be very clear about first two. If you have any doubts in RC circuit chapter, go back to the video done by Pradeep sir. Revise the derivation there also. And if you again have any doubt to me, you can ask right now. You can ask me later, or you can watch the video anytime. Okay, so if you understand these two, when we come back to AC chapters, the derivations will be easy. Okay, and AC chapter derivations are very important. They might not ask you, these two derivations, but there's a high chance they'll ask you in the AC chapter. Okay, am I clear, guys? I hope you don't have any doubts. Okay, if you have any doubts, that's also completely fine. Let me know. I'll explain it to you. Okay, so what's left in this chapter is very simple. I'll mostly take 5 to 10, 20 minutes to complete this chapter. Okay, so one is inductor in series, inductor in parallel, and other is generator. If I complete that, this chapter is over, guys. Okay, and in the next class, I'll be starting electromagnetic waves. Okay, so when we come back on Thursday, right? So the first 30 minutes, sort of it, I'll take it for what happens inductor in series and inductor in parallel. I'll take for this and we'll solve some problems on this. And I'll tell you what a generator is, how does generator work, what is a step-up transformer, and what is a step-down transformer. Step up and step down, I'll tell you this. After that, we'll move on to electromagnetic waves. And electromagnetic waves will not take more than 60 minutes. आराम से complete हो जाएगा. And one question is compulsory from electromagnetic waves for JEE and NEET. So there's one question mandatory. You will always see, and they're very simple. It's a theoretical chapter, just like chemistry or biology. It's a theoretical chapter. Sorry for saying it that way, but one question is very simple. And before you start your pre-board exams, I'll complete communication systems. And again, one question is compulsory from communication system, and even it's also theoretical chapter. Okay, hardly there is 4 or 5 formulas. Hardly. Okay. Yeah. So before your pre-board, we'll complete electromagnetic waves and communication system. So one class each. One class each. Cool. Yeah. Okay, so then try to work out the problem since because of time constraint, we are in the end of December. Okay, so hardly I might get few classes, right? In January, I may get 2 classes in the first week. Then after pre-boards, I may get again 5 classes. Okay, and in the month of February also, I may get again some these kind of classes. I hardly get 14 to 15 classes. Okay, so our time is very precious, guys. So in this 15 classes as much as possible, I'll be trying to complete as many syllabus as possible. So don't miss the class. Be very attentive. I'll be skimming out a topic like important topics only, which are very highly probable for JEE and NEET. Okay, so that is why I chose EM and communication system. Okay, the chances you get EMS is the question from EMS is very high. Okay, yeah. So will JNV open from January 4? Bro, Karnataka government have given order to open the state board school, but since JNV is a central government school, I don't think that order will be applying there. Okay, I'm not sure, bro. Okay, so we'll have a word with principals once. Okay, I'll talk to them and I'll let you know if there is any such thing. Cool then. Okay, guys. I'll be uploading the notes right now. Revise it, study them, be cool. Okay, cool, guys. Thank you for being here. See you later. Bye bye. Okay, Nathank. Bye. Okay, Anusha. Okay, Vandita. Bye. Bye, everyone.